I just had a challenge to start my lecture with something besides ladies and gentlemen by my wife. And even though she challenged me and I said I could do it, the first thing I wanted to say to you was ladies and gentlemen. Um, so I'm going to try to stay. I've already said it, so I guess I'm okay. Let me give you a little bit behind the scenes what happens with a lecture. I have underneath this very desk that you can't see, I have all my binders for thermodynamics. Say lords and ladies. Lords and ladies. Welcome. Welcome to thermodynamics. But anyway, what I was saying was underneath this there's this all my binders of thermodynamics has all this stuff, and I get on my hands and knees, I go underneath there, and I pick up these very notes. These notes today that show us that we are going to be talking about PVT relations for ideal gases, or for gases, not even got ideal gases yet. And it leads us to the ideal gas law. And this is exciting. This is new. This is fun. This opens up a whole other door. You might be thinking, Dr. Wenklin, does that mean that there are more tables in this appendices that I can use after this lecture? And the answer is yes. Yes, you can use more tables. My wife just whispered, it's all lies. Which it's not. It's not all lies. These people in this house don't respect me, and they don't respect my love of thermodynamics. I try every day. And you're saying to me, Dr. Wanklin, it's 1 minute and 9 seconds into this lecture, and all I've gotten is a drivel from you, and I don't want to hear it. I don't pay you for this. I pay you for solid thermodynamics content. So here it comes. Let's say we take a piston cylinder. Whoa, let's make it magical. We take a piston cylinder. Okay. And we're going to take this piston cylinder here, and we're going to fill it full of a gas. Okay, any gas. A magical gas. And we are going to move this piston cylinder to various equilibrium states. And when we get it to an equilibrium state, we're going to measure the pressure and the specific volume. Okay, so what we're going to do here is move it. And we're going to measure two things: pressure and specific volume. And we're going to do that at a constant temperature. So every time we do this, we want to keep the temperature of that gas constant. We can do that. We can keep it constant. We can add some heat to it to make the temperature constant, or we can remove some heat to keep the temperature constant. So at constant temperature. Okay, and let's see what happens if we plot that information. And so I'm going to draw a representative plot here. We are going to have on one axis, we're going to put pressure. And on the other axis, I'm going to plot this: pressure times molar specific volume all over temperature. Okay, PV over T. We do that for a reason, because if I do that, here's what happens to the lines. They look like this. Here's going to be my temperature 1. And then if I do a different temperature, maybe this is my temperature 2, and maybe this is my temperature 3, and maybe this is my temperature 4. Okay? And we can't go down to, no pressure, but we can extrapolate that. We can extrapolate that, which interpolate means between numbers, extrapolate means beyond the numbers. We can take that and look what happens to this. And it's kind of funky there what I've drawn, but we get it, and it all comes to a common point. Okay, you're saying, Dr. Winkle, look at your graph. It doesn't do that, but in real life, it would all come to a common point, and that's awesome, and that's unique, and that is universal. Okay, and we call this. We look at this point right here, and we say the limit as pressure goes to 0 of PV over T is equal to something specific. It all comes to a one point, and that is something we're going to call R bar. R bar is very special to us. R bar is equal to the universal gas constant. Okay, universal because it doesn't matter which gas we're dealing with. Constant because it's always the same value. It is common limit for all temperatures and all gases. It's universal. It's kind of amazing when you think about it. Doesn't matter what we do here. And the value for R is, R bar, is given to you in the inside front cover of your tables there. Let me see, does my, oh, I got the wrong one. This one has, well, I'll get to it in the break. I'll put it out here. But you can find it in your constants and conversions, in that conversions thing. You don't have to have it memorized, but I think by the time the end of the semester comes, you will have it memorized because we'll use it so darn much. It's going to be 8.314 kilojoules per kilomole Kelvin, or 8,314 joules per kilomole Kelvin. And then we have two versions in the English units. We have 1.986 BTUs per pound mole per degree Rankine, or 1545 foot-pounds per pound mole per degree Rankine. Okay, so basically the difference between these BTUs and the foot-pounds one. The foot-pounds one was converted to BTUs by dividing it by 776. So no big deal there. No big deal there. But that's the universal gas constant. And that's a very, very nice thing. Very, very nice thing. Now, going on beyond this, we can have something called the compressibility factor. Okay, so let's introduce this idea of the compressibility factor. And we're going to call the compressibility factor, we're going to call it Z. Easy to remember. Compressibility doesn't have a Z in it, so we're going to call it Z. And we're going to say that Z is going to be equal to PV over T and over R. R and T. PV over R and T. Let's do it this way, because this is probably how you've seen it. PV over R and T. Okay? Very similar to what we said up here. We said PV over T over R. Basically what we're doing is we're moving this R over here underneath that and setting it equal to something we're going to call Z, the compressibility factor. And let's see what the units are on compressibility factor. Okay, so let's just say pressure is going to be, let's do SI here. It's not going to matter. Well, let's just see. SI, pressure is going to be in kilonewtons per meter squared. Kilopascals is what we're going to say here. Units usually go in square brackets. Molar specific volume here is going to be in kilograms. Sorry, no. It's going to be in meter cubed per kilomole. Sorry, my brain just went haywire there for a second. Meters cubed per kilomole. Now, it would be kilograms if you were dealing with it at non-molar. Didn't have the bar over it, but now, since we have the bar over, it's a molar basis. Then we have our units for R, which I'm going to say are going to be kilojoules per kilomole times Kelvin. And then we want to keep our temperature in Kelvin. And let's see what our units end up being here. Well, kelvins are going to cancel. Our kilomoles are going to cancel. Meters are going to cancel here. And a kilonewton times a meter is going to be a kilojoule, which is going to cancel. And this is going to be unitless. So we've developed a unitless value called the compressibility factor. Okay? And that is going to be something that's going to be useful to us as we're going through our studies. Now, let's say, do we have to keep things in molar basis? Well, we know that molar specific volume is equal to the molecular weight, which we can find in table A1 or A1E, times the standard specific volume. Remember, molecular weight is going to be in, let's say, kilograms per kilomole. And our regular specific volume is going to be in meters cubed per kilogram. And we're going to see the kilograms here would cancel off, and we have meters cubed per kilomole. Okay? And I just want to mention here, this is, you can find this in A1 or A1E. Okay, now the same reason we can say R bar is equal to the molecular weight times something called R. Now, why this is going to be the universal gas constant, this R is going to be just the gas constant. It's a specific gas constant. Now, I'm using the word specific in a different way than I do specific volume. I'm just saying it's the gas constant for a single gas. Okay, a single gas. So if we take advantage of these and we put these two things into this equation up here, now we have Z is equal to P times molecular weight times specific volume all over R times molecular weight times T. And you can see that the molecular weight cancels out, and we can also put this as PV over RT. Now we're not using the universal gas constant, we're using that individual's gas constant. Okay, and so we need to understand that this R, this individual gas constant, is equal to R bar divided by the molecular weight. And we're going to do this calculation a lot. We want to find the gas constant for a specific or a single gas. We're going to say, okay, we're going to take the universal gas constant and divide it by the molecular weight. Now you could memorize or have a table full of gas constants, R's, but we don't provide those to you. We provide you with R bar, and we provide you with molecular weights, and you can calculate your value of R this semester, and you will over and over again. Okay. Now there is a table in your book, table 3.1, I think it does, that gives you this. It gives you all these R values, but again, you can't use that on the exam, so we're going to calculate it ourselves. Okay. So let's leave this at here. We'll start our next segment of the video exploring how we're going to use this compressibility factor idea.